Okay, today we're going to talk about covalent bonds, and there are two types of them. Remember that the word covalent, co means shared, valent is referring to the valence electrons, which are the highest energy outermost electrons on an atom. So the two types are non-polar covalent bonds, and that's when you have an equal sharing of electrons. So I'm going to define these and then we'll talk about them in a little more detail. And polar covalent bonds. Polar, like two poles on a battery or two poles on the Earth, the North Pole and the South Pole. It's referring to the magnetism of the Earth. Polar means that there's kind of opposite sides, or that there's a different charge on each side. So that means that there's an unequal sharing of electrons. Okay, there's these two types. And if you wanted to visualize this, it's easiest to use a Lewis dot structure. If we take chlorine, remember on the periodic table, here's our periodic table. Chlorine is one of our halogens, which is right here, which I know that you can't see very well, but you know it's in column 17 or 7A, so it makes it a halogen. So if it's in column 7 or 17, that means it has 7 valence electrons, and there's our Lewis dot structure. Okay, and then this other chlorine can come in there with its 7 valence electrons, its outermost highest energy electrons. And the goal is to get to 8, so we want a full valence. So the way that our two chlorines can do this is by sharing this electron. So now we have a structure that looks like this. With this shared pair in the middle, and this is a covalent bond. Again, covalent, sharing of valence electrons. And we said that with a Lewis dot structure, we can represent that with a hyphen that shows that shared pair of electrons. Okay. All right, so there's our covalent bond that we're visualizing. Now, if we have these two atoms, kind of regardless of what they are, then each atom is going to be pulling on that shared pair of electrons in either the same or different ways. Okay, so this chlorine is pulling on this shared pair of electrons this way, and this chlorine is pulling on the shared pair of electrons this way. Okay? Now, because these are both the same element, they're going to pull on these electrons in exactly the same way, right? We learned in atomic theory that atoms of the same element are identical to each other, so they're going to behave in the exact same way. If they're both pulling on that shared pair of electrons in the same way, that makes this a non-polar bond. So it's going to be an equal sharing. So anything that's paired with itself is going to be a non-polar bond. Now, just as a note, the covalent bonds, remember, are only between nonmetals and nonmetals. So when we talk about metals with anything else, or metals with themselves, then that's going to be a different type of bonding. So covalent bonds are just the nonmetals with the nonmetals. And if we're referring back to our periodic table, remember we have that stair step of metalloids over here. Everything to the left is going to be metals, and everything to the right are going to be our nonmetals. So when we're talking about covalent bonds, we're talking about this little corner of the periodic table here. And we're excluding the noble gases, because the noble gases already have a full octet, so they don't need to share electrons in order to have a full valence. That's that octet rule again. Okay? So that's non-polar covalent bonds. Let's talk about this unequal sharing of electrons, these polar covalent bonds. So if we have something like, let's say, hydrogen and chlorine. So hydrogen has 1 valence electron, it's in the first column. Chlorine has 7 valence electrons again. And so one way they can both have a full valence is for them to share an electron here. So now we have hydrogen, this shared pair in the middle. Chlorine has these 3 pairs that are unshared. Just as point of reference, these 3 pairs here that I'm highlighting with little bubbles are called lone pairs, and they're non-bonding. So we say that chlorine has 3 lone pairs of electrons, 1, 2, 3, and then it has that one place that it can make one bond, okay? So it has a full octet. It has 8 electrons around it. Let's look at hydrogen here for a second before we get into our polar covalent bonds. If we look at hydrogen, hydrogen only has 2. So it's an exception to the octet rule. It doesn't want 8. It seems to be happy with 2. So both hydrogen and helium are exceptions. Because the octet rule says broadly that atoms want to have a full valence. So they want a full shell that's the outermost and highest energy shell. And so for most elements, that's going to be the 8. But hydrogen and helium are happy with 2 electrons. And if you think back to what we learned in chapter 4 about the structure of an atom, then you'll realize that this is because the only orbital that hydrogen and helium have filled is the 1s orbital. So remember, there's only 1s. It's that spherical one, and it can hold up to 2 electrons. Okay? That's just kind of an aside. All right, so that kind of gets us into talking a little bit more about polarity. So we have a difference in elements, but just by looking at them, we don't necessarily know whether it's polar or nonpolar. They could still be equally sharing, even if they're 2 different elements. So in order to determine whether or not this is an unequal sharing of this pair right here, then we have to look at what is called the electronegativity. Apologize for all the rustling there. So electronegativity. It's got electron right in the word, right? Here's electron, electronegativity, and the electronegativity is a measure of how greedy, this is the way I like to define it, how greedy an element is for electrons. And we're going to put greedy in quotes there, because of course we're anthropomorphizing a little bit. Elements aren't actually greedy for anything, but energetically speaking, it's lower energy if it has more electrons, is what we're trying to say, that it's happier if it's pulling on these electrons that are shared. Okay, so the general trend in electronegativity, if I was to draw kind of my schematic of my periodic table here, right, so here's just a general periodic table. I didn't put all my divots in there, but if this is the periodic table, then we have an increasing electronegativity going from left to right. So I'm going to put increasing En here. Capital E, capital N is usually the way that we abbreviate electronegativity. And we also have increasing electronegativity going up the columns. So the general trend then, if we're looking at how this all relates, is that we have lower electronegativity over here, and then as we go up to this corner, then we have higher electronegativity up here. And if we relate this to our periodic table, then we can see that, and maybe you can't see all that well, but these are our alkali metals over here and our alkaline earth metals, that francium and radium over here are going to have the lowest electronegativity, lowest meaning that they want to pull away those electrons less than the other elements, and fluorine, oxygen, and chlorine over here have the highest electronegativities. Now again, I'm disregarding my noble gases here because the noble gases already have a full valence. They don't want to rip away electrons from anyone. So when we're considering our electronegativity trend, we kind of ignore the noble gases. As we do for most things, because the noble gases have this full valence. They're really inert because they don't like to interact with anything because they have the full valence. So this is kind of what we're working with here. Okay, so the way that we can use electronegativity is there have been very smart scientists in the past that have put together numbers for these measures of how greedy elements are for electrons, so how much they're pulling on that bond one way or the other. So if we go back to our hydrogen and our chlorine here, So chlorine is pulling on it this way, hydrogen's pulling on it this way. Which one is pulling on it more? Well, we have to go to our electronegativity values, and there's a table for that. And it was first put together by one of my favorite historical chemists, and we'll get to him later in the quarter, but his name is Linus Pauling. So it's the Pauling electronegativity scale, which is what we use in order to determine the type of bond that we have. So we have a nonmetal with a nonmetal. We have to go to this table of electronegativities to determine what the values are, and we can use them to figure out what this bond is. Okay, so the way that this looks is like this. There's our Pauling electronegativity values, and there's one like this that's in your book as well. So you'll find this in your book. It's at the bottom of one of the pages. I don't have it in front of me, but it's in this chapter. You'll find it, no problem. So each of these values, and this is never something that I would have you memorize. I will always give you this table should you happen to need it. If you look at these values, you can see that they kind of range from smallish. So here's rubidium down here. They don't even have francium or cesium. So here's rubidium at 0.8, right? And if you kind of move upward, you can see that the greatest number that we have up here is fluorine with 4.0. Okay, so again, our most electronegative elements, oxygen at 3.5, fluorine at 4.0, chlorine at 3.0. Those are our most electronegative elements. And then as we go further away from that, either down the columns or to the left, then we can see that the numbers get smaller. That means that this side of the periodic table, our nonmetals tend to like to pull electrons away from our metals. Okay, so nonmetals tend to be a little more greedy than the metals do. Okay, now when we're looking at covalent bonds, we're just focused on the nonmetals. So we need to figure out a difference within elements that are already fairly electronegative. So let's talk about how we do that with our example. So if our example again is HCl, and we go to our table, then hydrogen's up here at 2.1, and chlorine is over here at 3.0. Now what I can do, and the way I can use this Pauling's electronegativity scale, is I take the difference between these two numbers. So if I'm taking a difference, I'm subtracting. So I subtract the smaller one from the larger one. Or you could think about it as taking an absolute value if you prefer. You always need to end up with, as an answer, a positive number. So I take the difference between these two, and I get 0.9. Okay, now because I'm on a 4-point scale, if I'm above 0.4, so anything greater than 0.4, is going to be a polar covalent bond. But there is a ceiling to this, because there's a point at which it becomes so polar that it ends up losing electrons. And so the range for polar bonds is greater than the 0.4, but less than 1.7. Okay, and that gives you a polar covalent bond, is this range. So we take the difference between the two values, smallest from the largest. That number here is going to give us information about the polarity of the bond. If it falls within this range, then it is polar. So in this case, this is a polar covalent bond. Let's look at another example. If I take, let's say, nitrogen and chlorine. So if I have a bond between nitrogen and chlorine, and again, this is out of context. This is just a bond between two elements. This isn't looking at anything else that's going on, and we're just starting to talk about bonding. So if you look at this here, we're just looking at nitrogen and chlorine regardless of anything else that's going on around it. So we already looked up chlorine. Chlorine is 3.0. When I go to my electronegativity scale here, I see that nitrogen is also 3.0. So just looking at that, I should say, all right, well, there's no difference between them. And if there's no difference in the electronegativity, then it means they must be equally sharing them. And again, you can confirm that by just taking the difference, because they're the exact same number. That gives you 0, which is less than 0.4, and anything that is less than 0.4 is nonpolar. So what this means is that there's so little difference in the way that they're pulling on these electrons, chlorine pulling this way, nitrogen pulling this way. There's so little of a difference between the way that they're doing that they're basically sharing them equally between the two. Okay, that's what that difference tells me. Okay, so let's look at another example here. Let's take hydrogen and phosphorus. Okay, so if we look at hydrogen and phosphorus, again, it's a nonmetal with a nonmetal, so I can automatically say nonmetal with a nonmetal is a covalent bond. But what type of covalent bond is it? So now we go to our Pauling electronegativity scale. We already saw that hydrogen is 2.1. If we go to phosphorus, phosphorus is down here in the nitrogen column below nitrogen, so phosphorus is 2.2. So if you take the difference between these, again, you always take the smaller one from the larger one. It gives me a difference of 0.1. That 0.1 is less than 0.4, so that means this is a nonpolar bond, equal sharing. Okay. So this is how we use those electronegativity values. And again, this is useful when we're talking about covalent bonds, because covalent bonds are always between nonmetals and nonmetals, and then we're looking at the difference in the electronegativities between the two elements in order to see whether or not they share them equally, covalent, equal sharing, or unequal sharing. And remember, the way to remember polar is that polar bears don't like to share. So if that helps you, then hopefully that'll help remind you as you're going through and doing these calculations. Now this isn't super high level math, we're just taking the differences here, but again, I do want you to know how to use this table and not necessarily have it memorized. A useful thing to know though would be that trend, that as you go from the left to the right, that you have increasing electronegativity, and as you go from the bottom to the top, you also do as well. Okay? If you have any questions on this, just let me know. Otherwise, I'll see you